Welcome, everyone. Thank you for joining us today. My name is Alyssa Tay, and I'm with the Collaborative for Health and Environment, also known as CHE. Please feel free to introduce yourself in the chat if you'd like to. We are pleased to be hosting this webinar in partnership with our colleagues at PSNAP, the Physician and Scientist Network addressing plastics in health. We'll share the link to PSNAP in the chat as well. I'm delighted to introduce our speakers. We're really looking forward to this conversation with Dr. Veena Singla and Dr. Nihan Karali. So before we begin, I'll quickly share a little bit more about them. Dr. Singla is an affiliate at the University of California, San Francisco, and a senior fellow with the Halt the Harm Network. Dr. Singla's work seeks to address health disparities linked to harmful environment exposures using an interdisciplinary approach incorporating environmental health, exposure science, public health, and policy expertise. Dr. Karali works at the intersection of energy, material, and environmental impacts of industrial production systems. Dr. Karali focuses on identifying sustainable, non-polluting, and safe pathways for industrial production and consumption, including plastics production and recycling. We're really honored to have both of you with us today. We'll be hearing from Dr. Singla first, followed by Dr. Karali, and then we'll have a few minutes of Q&A, led by my colleague, Dr. Rachel Massey. So with that, I'd like to hand it over to our speakers.
Thank you so much, Alyssa, and thank you to CHE and PSNAP for hosting this webinar on this important topic. The work that I'll talk about today is supported by the Schmidt Family Foundation funding, and I have no conflicts to disclose. So the plan for what I'll cover is I'll talk a bit about the plastics life cycle, give an overview of that and recycling in general, and then cover the basics of chemical recycling. What is it? How does it work? And then I'll go into a little more depth on health concerns with some of the different types of chemical recycling technologies. And as Alyssa noted, we should have some time for Q&A after the presentation, so please feel free to drop your questions into the Q&A as I go along, and hopefully we'll have time to address them at the end. Okay, so some important background that will be helpful for what I'm going to cover on chemical recycling is just to understand the basic life cycle of plastics. So most plastics are made from fossil fuels, and there's harmful emissions and environmental exposures associated with fossil fuel extraction and chemical manufacturing. The basic chemical units that go into plastics are called monomers. You can think of these as like the individual beads that would go onto a necklace. And some of these monomers are themselves toxic and harmful chemicals. So examples are styrene and vinyl chloride, which are both cancer-causing chemicals. Those individual units, those monomers, are linked together into the plastic polymer. So you can think about that as like stringing beads together onto a necklace. And in that process, there can also be harmful chemical emissions and releases. And some examples of polymers, plastic polymers, are polystyrene, polyvinyl chloride, also called vinyl or PVC. So you know that's the polymer because of the poly in front of the name. And then to those polymers, additional petrochemical additives help to give the plastic other properties like color. So pigments can be added, flexibility, adding plasticizers like phthalates, flammability properties, adding flame retardant. So these petrochemical additives, many of those are themselves toxic and harmful chemicals. And overall, we know there's more than 16,000 different chemicals that are involved in this whole process of making plastics from the fossil fuel feedstocks. So then the polymers along with the additives can then be further processed into plastic products. Okay, so that's the first part of the plastic life cycle, how plastics are made, then products are used, and at the end of life, most are disposed either by landfilling or incineration. Some leak into the environment, and a small amount of that plastic is recycled. And that small amount that is recycled, it happens by this method called conventional or mechanical recycling of plastic. So in this process, plastic waste is collected, it's sorted by type, by the type of polymer, it's cleaned, it's shredded, it's made into these plastic pellets, and new plastic products can be molded from those pellets. So we know plastic recycling has issues. Not much plastic is recycled, but whatever is, it's happening by mechanical recycling. Okay, chemical recycling. It starts out looking similar to mechanical recycling. You collect plastic waste, you sort it by type, clean and shred it, and then the chemical recycling technologies look a little different. So these technologies, there's a number of them, and I'll go into more detail on kind of what those are and how they work later, but they all have in common is that they're using heat, pressure, chemicals, or some combination of those things to actually break down the plastic to some degree. And what the broken down plastic can be used for also differs. So it can be used as a fuel, and the chemical recycling technologies all have air emissions and generate solid and liquid waste to different degrees. And those fuels can be burned for energy. So that's one option for chemical recycling. The broken down plastic can also be used as chemical components. Again, there's air emissions, solid and liquid waste generated. And those chemical components can be used to make other chemicals, other chemical feedstocks, and can also be used to make new plastic. So kind of different pathways here for how the products of chemical recycling can be used. So I think one really important point is that this top orange pathway, the fuel, and then the fuel gets burned for energy, that's not recycling. So here in this diagram, you can see depictions of a circular and linear pathway for a material. You start with the virgin material extraction, processing, you produce the product, use the product, and at the end of life, it can return into the material cycle through these various pathways, like use extension, redistribution, or recycling, or it can be disposed, exit the pathway through incineration or landfilling. So if it's burned as a fuel, it is exiting this materials production cycle. It's not available to re-enter the cycle, and that means you need to extract more virgin resources. So the benefits of recycling really come when you're able to replace some of that demand for virgin material. You can think about paper that's made from trees. If you recycle paper, it can be made into new paper, and you don't have to cut down as many new trees. So that's the benefit of recycling. If you burn the material, you lose all those benefits. So when chemical recycling is generating fuels that are burned, calling it recycling is really a misnomer. It's not recycling any plastic, and you don't get any of the benefits of recycling by turning plastics into fuels. Okay, well, another important point about mechanical and chemical recycling of plastics is that neither one of these is addressing or diminishing these upstream emissions and harms that are associated with making plastics. So those remain, whether you're talking about mechanical recycling or chemical recycling. And both mechanical recycling and chemical recycling in the process have microplastic emissions. So microplastics are generated when you're processing, shredding that plastic. And the toxic chemicals that are part of the plastic can carry forward through the process into the recycled plastic or as emissions in that process, which I'll talk more about. Okay, so chemical recycling, I think, is confusing in a couple ways. The terminology is part of it. So one is that there's all these different terms you might have heard: advanced recycling, molecular recycling, waste to value. There's a number of terms that are used interchangeably that all mean the same thing. There are these umbrella terms for this collection of different chemical recycling technologies. So there's different processes like pyrolysis and gasification, solvolysis, solvent-based purification, and others. Okay, so there's those different technologies, and we can put them generally into two main buckets. The thermal conversion technologies, which are considered incineration under the Federal Clean Air Act. So that's pyrolysis and gasification, and pyrolysis of different kinds, such as plasma, arc, or microwave. They're all these thermal conversion processes. The other bucket is solvent-based technologies, which are not incineration. This includes solvent-based purification, solvolysis, which is also called depolymerization sometimes. And then there's different types of solvolysis that use different solvents, such as methanolysis that uses methanol, glycolysis that uses glycol ethers. So you might hear about different flavors of solvolysis that use different solvents. So I think the other confusing part about the terminology is that these terms can be used differently by different sources. It's not super consistent or standardized. So for example, sometimes pyrolysis might also be called depolymerization or thermal depolymerization. So I think that's something to be aware of, is that there's not really standardization in how some of these names and technologies are called. Okay, so now we'll take a closer look at some of the most common chemical recycling technologies, and there's health concerns associated with all of them. Okay, pyrolysis first. So this is the majority of operating and proposed facilities, about 80% in the US. And of that, the majority of pyrolysis facilities are being used to do the plastic to fuel process. Pyrolysis, it can't take all different kinds of plastic polymers. It can generally take polyethylene and polypropylene. So you can think of your like laundry detergent jugs, that's high density polyethylene, or your yogurt tubs, often those are polypropylene. So again, you get that plastic waste. It needs to be sorted by type into the types that pyrolysis can take. And then that's going to be broken down with high heat pressure, sometimes chemical catalysts, into these chemical components, these plastic breakdown products, as well as generating waste and hazardous waste in the process. Some of these plastic breakdown products are then burned to provide more energy to heat the process, because it is a high heat process. And some of them can go on to make this intermediate product, pyrolysis oil, which needs to be further processed to use as fuel or as a chemical feedstock. That waste and hazardous waste must be disposed, most often by landfilling or incineration, and hazardous waste must go specifically to hazardous waste disposal. Okay, so we see that a few plastics pyrolysis facilities in the US have generated large quantities of hazardous waste over the past few years. So here down the left-hand side, we're looking at 3 different pyrolysis facilities, and then the table shows the pounds of hazardous waste that they reported generating to the Environmental Protection Agency in these different years. And collectively, it was more than 2 million pounds over these 4 years. This is certainly a concern for the communities where it's generated, but also more broadly than that. So what we see is here this article is focused on the Braven pyrolysis facility in North Carolina and an investigation by the North Carolina Department of Environmental Conservation that found hazardous waste violations and issued the facility an imminent and substantial endangerment order. So what we see, again, this hazardous waste generation can threaten the community around the facility in terms of potential leaks and spills, emissions, the storage of that hazardous waste, but also when that hazardous waste is transported for disposal, all those communities that it's transported through, as well as the ultimate disposal site, which is generally incineration. So we've seen the consequences of transportation incidents with hazardous chemicals, like in the East Palestine, Ohio train derailment. And these hazardous waste incinerators are generally located in communities that are disproportionately low income or people of color or both, often already have burdens of industrial pollution. Okay, pyrolysis facilities also generate health-harming air pollution. So here we're looking at an excerpt of hazardous air pollutants that pyrolysis facilities are permitted to release. Looking at state permits for pyrolysis facilities in the US, you see the chemicals down the left-hand side, the different health hazards they're associated with across the top. So overall, these facilities are permitted to release more than 30 different toxic chemicals. They include chemicals like benzene, known carcinogen, lead that's damaging to the brain and nervous system, and more. And these chemicals are associated with increased risks of serious diseases like cancers, asthma, heart disease, and others. Pyrolysis units also present acute risks like fires and explosions. This article was covering fires and other dangerous incidents at a pyrolysis facility called Brightmark in Indiana. And these risks are also documented in the scientific literature, where we see explosions, fires, worker injuries at pyrolysis plants in Denmark. That's the top article, and in South Korea is the bottom article. Okay, so as a scientist, I have to have at least one slide that's really hard to read. So here you go. This is looking at the solvents used in solvent-based technologies. And the point here is not necessarily to read this whole thing, but just to know the solvents down the left-hand side are solvents used in solvent-based purification and solvolysis processes. And then you can see across the top is all the different health hazards they're associated with. So this presents concerns for emissions from the facility, exposures of workers who work at these facilities, as well as the generation of hazardous waste related to these solvents. Okay, solvolysis, the way this works is it can take one type of polymer input. Generally, it's polyethylene terephthalate, that's like PET, your water bottles, or polyester textiles. And so again, it needs to be sorted to that type, cleaned, and then that polymer is broken down with these solvents that are themselves hazardous chemicals. You get these chemical components of the polymer, as well as all the additives and potential byproducts of this process. The chemical components are separated away from the unwanted chemicals. That intermediate product, those chemicals then undergo further processing. They can be used as chemical feedstocks. They can also be used to make new plastic polymers. The process also generates waste and hazardous waste, which needs to be disposed most often by landfilling or incineration. And I don't have an example from a solvolysis facility to talk about more specifically, because there's only one potentially operating in the US, Eastman Chemical in Tennessee, but it's part of a larger complex, so we don't have much information that's publicly available on what the chemical recycling portion of that facility is actually emitting or generating. Okay, solvent-based purification. This is also called plastic to plastic or physical recycling or dissolution precipitation. Here again, the input needs to be a single polymer type, not mixed plastic waste. For example, like polypropylene, you get that sorted clean plastic. Again, you're going to dissolve the plastic with solvents, and through this solvent-based process, you get the polymer and additives, and try to separate away the polymer from those additives and other byproducts. And that polymer can then be used to make new plastic. Process also generates waste and hazardous waste that needs to be disposed most often by landfilling and incineration. The solvent-based purification facility PureCycle in Ohio generates air pollution and hazardous waste. We see it's permitted to release volatile organic chemicals, or VOCs, from the facility. They're required to burn off excess VOCs, which can also generate particulate matter and other harmful air pollutants, and the facility generates hazardous waste. Overall, what we see with these chemical recycling facilities, the ones that are currently operating or partially operating, and the ones that are proposed or under construction, is that they're disproportionately sited in communities that are low income or people of color, or both. So again, environmental justice concerns, many of these communities are already burdened with industrial pollution. Okay, so in summary, I've given you a lot of information about different chemical recycling technologies and some health concerns, and I'll just sum up some of the things in common and patterns and trends. So what we see is that on the ground, the facilities are mostly pyrolysis facilities, and they're mostly being used to make fuels and not recycle any plastic. There's a lack of transparency. I mentioned for solvolysis in particular, we don't have much data on what's happening at the facility. All of these technologies generate harmful air pollution, and they all do one or more of these things. They're using hazardous chemicals, they're producing hazardous chemicals, they're generating hazardous waste. Some of them are doing all of these things. We see they're not operating at scale, and Dr. Crawley will talk more about some of the technical issues here, and generally cited in marginalized communities. So thank you very much, and I will drop some links in the chat to other work that I've done on chemical recycling life cycle assessments, which I didn't have time to talk about today, but that you can check out that report. And I will pass it to Dr. Crawley.
Hello, everyone. Let me share my screen. first. All right. I also would like to start thanking Jay and PSNAP for having us talking today about chemical recycling. With that, I'm going to talk about chemical recycling, but from the lens of specifically technical limitations and what the technical data and current literature actually tells about its potential, which has a direct link on our a direct relation to recycled content discussions we are currently having. So before I begin, I should note that this presentation reflects my own views and does not represent the view of any institution. So I want to start with going over some background information, and with that, like looking at the plastic production growth in the last 2 decades and the projections for the future, and what recycling portion of the production. So what we see here is plastic production was to 460 million metric tons in 2019, and the annual average growth rate was 3.6% between 2019. And industry experts suggest that this demand will continue and it will grow like between 2.5 to 4%. There are even some higher expectations from some reports published recently. So, which means the plastic production could either double or triple from 2019 levels to like almost 1,000 million metric tons to 400 million metric tons by 2050. So, this is a production growth story, but it's not just a supply story, it's also a waste trajectory. So more production means more waste, and which we will need to deal with, or that will accumulate in landfills or lead to the environment or will be incinerated, right? Um, so if you look at the recycling rate in 2019, you see that recycling was roughly about 6%, right? And in almost all of these recycling came from mechanical recycling. This shows us that how fundamentally linear actually the plastic production value chain is. So despite the increasing recycling efforts, so this number reflects 2019, but current numbers are not significantly different, like maybe 8%, 9%, but not significantly different. So if you look at the donut chart on the right-hand side, you see like three types of polyethylene, polypropylene, PP, PET, polyethylene terephthalate, like PVC, like polystyrene PS, ABS, SAN, like polyurethane. Those are very common plastic polymers you could see in the market. These actually account for almost 80% of the plastic production in 2019. And these are the polymers that any recycling system, it doesn't matter mechanical or chemical, that needs to handle. Circular economy policies and the global ambitions, right? With this growing waste problem, governments worldwide enacted ambitious recycled content mandates and EPR schemes. So in recent years, so I have a couple of examples here, a few examples, like EU has this packaging and packaging waste regulation that requires 25 to 30% recycled content in plastic packaging by 2030. California SB 54, which has 65% recycling rate target for single-use plastic packaging by 2030. Japan's 3R and Plus Renewable Initiative asks for 60% reuse recycling target by 2030, including plastics. China also has different national targets for recycling rates and resource efficiency, including plastic products. Beyond these individual countries and states, like there's also EPR schemes are expanded across the globe that also supports recycling contents in plastic products and plastic packaging. But here it is, the problem. The mechanical recycling faces well-known limitations, Like Vina was mentioning, like there is serious contamination sensitivity, there is significant material quality loss. Like you could only recycle 1 to 2 times via mechanical recycling, and then it will go to downcycling and eventually will be waste. But chemical recycling, the chemical recycling is the solution because it is promoted as a solution to mechanical recycling limitations. But we see that the problem, as I will actually show in the next slide, most of these limitations are not solved by chemical recycling. They just reappear in different forms. So what is exactly chemical recycling? I'm kind of repeating what Vina was going through, but I think it's important, like we remind ourselves again what chemical recycling and different types of it are. So chemical recycling uses chemical processes to break down plastic into constituent parts, right? These parts could be hydrocarbons or monomers or oligomers, and some processes uses solvents to separate additives from polymers. So the output products can go into 2 different directions. In a closed loop direction, covered products are used to manufacture new plastics. And in an open loop direction, they can serve as alternative chemical feedstocks for different chemical products production, or they may be used as fuels. So the schematic here is showing plastic production chain and closed loop chemical recycling interaction with it, right? So there are 3 types of chemical recycling I have in the boxes here listed: thermochemical recycling, depolymerization, and solvent-based dissolution. But like Vina was mentioning, there is no agreement on the literature on terminology, right? Like she said, depolymerization is also called solvolysis, right? And thermochemical recycling is incineration in some reports and rules. And solvent-based dissolution, sometimes called purification, just purification. So what happens here is, like this picture shows, like the waste comes, if it is thermochemical recycling, with heat, we break the polymers into small hydrocarbons and then use these hydrocarbons to manufacture monomers, and eventually they turn to polymers and then the plastic products. In depolymerization, it's 1 step above. We depolymerize the polymers into monomers, and then we use them to produce polymers and eventually plastic products. And in solvent-based dissolution, again, 1 step further, because at this time we try recovering polymers, this process. But so each technology targets on a specific polymer types. This is not like every chemical recycling technology can work on all polymers we are talking here. That's not the case. And this table actually shows some examples of these processes, which polymers they are applicable, which is challenging, on which they're challenging. There's also this common misconception. I know you also mentioned this. The chemical recycling is like perceived as a single technology, but in reality, it is a family of distinct processes, with each of them designed for the specific chemistry of particular polymers. Like if you look at this table, like solvent-based dissolution, it actually works on most of the common polymers, and then the recovered product is polymer again. Depolymerization only works on PET. I want to say there is some research on PU depolymerization, but nothing on even in pilot scale, to my knowledge. Like Vina was mentioning, so depolymerization uses different solvents to break PET polymer into monomers, and then based on which solvent it's used, the name of the process can be different, right? So I have here defined enzymatic hydrolysis, methanolysis, and glycolysis, like 3 most famous depolymerization technology currently we have for PET. each of these recover different monomers from poly PET that can be later used for repolymerization of PET. In thermochemical recycling, we have pyrolysis and gasification as main categories. And then these, like I said, they work on again, not almost all, but most of the common polymers on the market, with some exceptions in both of them. But like pyrolysis cannot have PET, PVC, or ABS and PU. And the mix, like I'm going to talk about this in the next slides. Similarly, gasification cannot have PVC and ABS in the mix. So contamination, right? So when we talk about, like in the previous slide, like some of these polymers cannot be in the mix when we are processing either single streams or acceptable polymers mix for some of these chemical recycling types. The main problem is contamination. But we're talking about the contamination can create different problems for the recycling system and the recycled material. So we're talking about actually, I have two bullets here, but we can call it three distinct problems. Like contamination can reduce the process efficiency, that's one. It can create direct safety hazards, that's two. And then the third one, this is the recovered product. The recovered product can carry some chemicals or materials that can create safety problems in the next step, which actually defines the substitution rate of the recovered product with the counterpart virgin material, right? So what can be the sources of contamination? We know like food residues, detergents, labels, adhesive dyes, these are very common in our plastic products. Also, we collect most of the plastic product as mixed streams. There is also 16,000 plus chemicals, additives used. So those are again contamination sources. And some of those polymers carry heteroatoms. So these heteroatoms are defined as the atoms that are not carbon or hydrogen. Because carbon and hydrogen comes from fossil fuels and therefore they are called hydrocarbons, right? So these heteroatoms, especially in pyrolysis, like oxygen creates safety issue. Like Dina mentioned that the fire incidents happen in pyrolysis plants. This is mainly because of the oxygen involved in the process. Like polymers like PET has oxygen in it. So if mix includes PET, if it's not sorted out, that's the reason for fire. Similarly, chlorine, both pyrolysis and gasification, it can have a corroding impact in the downstream equipment, the recovered output used, right? So all of these things define what's the substitution rate eventually. For pyrolysis oil from pyrolysis, literature indicates 5 to 20% substitution rate with the virgin naphtha. This depends on the purification of the final pyrolysis oil. That's why we have the range. Solvent-based dissolution and depolymerization, they are blended with the virgin product like up to 30%. But this is not just because of contamination issue, but they also have material degradation impacts of these blending requirements. And I'll talk about that in a bit. And if you're going to use the product for food contact applications, in general, because of contamination, we have to either dilute it even more with the virgin materials or purify more and more. But this is really difficult, the purification, because like I said, like 16,000 plus chemical additives used in plastic product, and there is no tracking of them. So if you cannot provide something you don't know exists there, right? So the second problem, like contamination is a barrier, but the second problem is the material degradation, right? So each recycling we do creates a damage in the molecular system, and these damages are not recoverable. They accumulate with each cycle and progressively degrade the material performance until a level that it is not acceptable. So this is important because it defines the ceiling on how many times a polymer can be recycled before it hits this level of unqualified. So for context, for example, mechanical recycling hits that ceiling the fastest, 1-2 cycle. But solvent-based dissolution and enzymatic hydrolysis or glycolysis extends this to 3-4 cycles. But after that, they are again below the threshold of accepted quality. So which means we have to actually need to blend these recovered products from these chemical recycling processes with the virgin materials to have the quality we needed for the final product. Otherwise, it will come to a point they will downcycle and then will be waste again. So pyrolysis and gasification, they bypass this degradation because they break polymers to basic hydrocarbons. But like I said, there are severe contamination constraints in the final product which are recovered from them. So process efficiency, which is the material loss, is the other barrier. So what this mean is this, this each stage of the recycling, it starts from the pre-treatment in the material recovery facilities. You're losing a part of the material you start with. And then this happens in the entire recycling value chain. So starting with pre-treatment, for example, like where you sort, wash, dry, clean, and pre-process the product, the typical loss range is 5 to 30%. So this is a significant fraction of the waste stream already eliminated before even the recycling process starts. And depending on what type of chemical recycling process we are using here, the material loss could be 15 to 60%, right? And after that, what happens is, again, this is a repetition, but now we have this recovered product. We either need to blend it with the virgin material, so or purify it significantly as much as the knowledge we have what to purify, right? And so there is this blending happening there. And then sometimes some of these chemical recycling processes, the yield recovered, the recovered yield is insufficient for the next step for repolymerization. We again need virgin material. This is not degradation, this is not contamination, but simply because the yield is not enough. And then the yield is not enough because we are losing a part of the product, material loss. And when we look at the final product, we see that recycled content could be between 5 to 30% for most of the cases. I actually have some examples listed here in this slide. This is from the literature collected. Like it shows like pyrolysis oil, which goes to steam cracker, but 5 to 20% range, depending on how much purification is performed, and the rest is coming from virgin materials. Solvent based dissolution, doesn't matter polyolefins or other common polymers, they are blended up to 30% with the virgin material, so like high rates of virgin materials. The depolymerization types, the blending rate changes differently, again, depending on how much material you lose there and how much monomer you recovered. Yeah, the other thing I want to talk about is I think the last thing I want to talk about, this chemical recycling pathways are energy intensive. And the energy burdens of each process actually differ substantially. It reflects what physically it takes to break down and reform polymer chains in each technology, but also depends what kind of chemical we are using there. So if you look at solvent-based dissolution, you'll see actually there is the solvent-based dissolution process, but you're also using these solvent anti-solvent pairs, which most of the cases very energy intensive to produce, particularly for PT, PVC, and PS. There is research on alternative low-energy solvent pairs, but there is no commercially proven option at scale yet. If you look at pyrolysis and gasification, these processes, they are itself require really high temperatures, which means really high energy demand from these processes. And after that, the purification step is an energy intensive step, and how many times you do it, depending on that, again, you're increasing your energy footprint. So there is this purification paradox. I call it like, we wanted to achieve higher substitution rates, which demands higher purification, but it comes with higher energy consumption. Each time you purify, um, you consume more energy, right? And then it's not like you purify something in this like multiple chemicals in the same step. You purify each one of them individually in different steps. If you look at gasification, the syngas is used, which is the hydrocarbon we recovered from gasification. In the next steps to produce monomers and polymers, these processes are also very intensive. The syngas is synthesized in general physiotropes or methanol to olefin processes. These are again very intensive processes, particularly methanol to olefin. This requires methanol production, which is also energy intensive material to produce. Sorry. Similarly, this is the polymerization technologies we have there. If you look at them, they differ with their energy consumption profiles. Like the processes itself, they consume some energy, but enzymatic hydrolysis requires a secondary treatment, which is again another energy footprint there. Methanolysis use methanol, like I mentioned before, like in the previous slide. Methanol is produced from coal and natural gas in energy intensive ways. Methanolysis has a lower energy print compared to others. However, it has this yellowish tint with contamination issues, particularly for food contact applications. So this, I want to show that, before we get to the conclusion, I would like to have a perspective of greenhouse gas emissions, right? So this slide shows like primary plastic production already accounted for approximately 2.24 gigatons CO2 equivalent, which is roughly 5.3% of global GHG emissions in 2019. Well, for context, this is nearly 4 times the annual emissions of global aviation, right? And under 2.5 scenario, this emission footprint could be double, and until 4% annual growth scenario, it could be triple by 2050. So there is the central question, right? We know the chemical recycling technologies, they have an energy footprint, and some of them are very energy intensive. There's always virgin material blending requirements. So it's not just whether chemical recycling processes process the waste efficiently, but also, is it actually displacing virgin production at a meaningful scale? So we have the emissions reducing, or is it opposite? So with that, I wanted to conclude. I might be over time, right? So the conclusion is chemical recycling in its current form could not be a viable technological path if you're imagining a true circularity, simply because of the physics and chemistry of these processes require. So the 4 barriers I have walked through today that are not independent problems with independent solutions, right? They compound each other. So I'm listing here again, like contamination limits substitution rates, which drives the need for more virgin material. It's also a problem for safety. Material degradation limits the number of cycles, which means even successfully recycled plastics eventually exist the loop if it's not blended with virgin materials. There is substantial energy and chemical demands in most of these processes, and this cascading process losses at every stage reduce the yields significantly. Yeah, So with that, I would like to thank everyone again. And if you have any questions, follow up, can take it. Thank you so much.
Wonderful. Thank you so much to both of you for these excellent presentations and for all the really important work that you're both doing. So I see a number of good questions in the Q&A box, and some of them are they range from general to very specific. So let me start with one of the quite specific ones. So I'll read you this question. Are there any forms of chemical recycling that are at all beneficial from an environmental, climate, or human health viewpoint? There are claims about environmental benefits and circularity, but they all seem like versions of the same problematic processes. And then this person asks about two specific technologies, and I'm not going to read the full description or the brand names, but I'll just say one of them relates to carbon nanotechnology and pyrolysis-based recycling. And then one of them involves a proprietary mix of biological enzymes and other details. Um, so, yeah, Dr. Singla, would you like to comment on that question?
Yes, thank you so much. It's a really good question, right? That often when I'm speaking about these technologies, questions like this come up. That okay, well, the current technologies are problematic. Couldn't we have some better versions, some innovation? And the answer is yes and no, in the sense that absolutely, there can be some improvements around the toxicity of the current processes. So, for example, the process that uses biological enzymes and not toxic solvents is slightly better. You're using less toxic materials. And a major part of the issue with plastics is simply the toxic chemicals within plastics themselves. So the problem is what's going in, all of the toxic chemicals related to in the plastics related to plastics, and those come out in some way, in some form, right? So they can come out as emissions, as releases, as hazardous waste, as contamination in the recycled products. So yes, you can tweak and mess with some of these technologies to improve them and try to make them less toxic. And when you're talking about these fossil fuel based plastics as they're currently composed, all of these technologies and any new technology that's developed is going to have the same challenge of dealing with all these toxic chemicals that are in plastics. So fundamentally, we really have to get these toxic chemicals out of plastics if we're going to try to manage them in a safe way at the end of life.
Thank you so much for that answer. Looking at other questions that have been posed here. So there's a question, can you address how these processes may contribute to climate change? And Dr. Karali, you did address that in your slides. I don't know if Dr. Singla, do you want to say more about it, or would either of you like to add a little more?
Yes, I think there's a upcoming publication about that, but it's under review, so I will and I won't be able to share any results. But what I want to say is these processes, most of them are energy intensive, and the ones that are not energy intensive could be um, like if we want to do this closed loop, like we really repolymerize and then we really get to the plastic product back again, they are at the same ballpark. And then the fact that we always need virgin materials, virgin plastics mixed up makes that footprint could be actually even higher, right? So it's not like you are doing this process and it's slightly less energy intensive, maybe, but then you're mixing with the virgin material, so you're kind of canceling everything out, right? And then, like in 3 cycles, whatever you're mixing is actually gain waste, and then you're starting new, right? So there's so many factors impacting that, and what I see in my, like research or my understanding is that most of the cases because of virgin material blending or the chemicals are used because we are looking at this from systems portfolio, not just recycling itself, right? Because these recycling processes need solvents, different chemicals, right? They also have their own footprint. So if you look at this from a systems thinking perspective, like it's highly likely they increase the emissions more or at a similar level, right?
And if I could just add to that briefly, I had dropped some links into the chat on the analysis of life cycle assessments that I had done recently. So, thinking about the overall climate footprint of these technologies, it's absolutely, as Dr. Crawley said, the energy that's used, the inputs that go in, right, the solvents and chemicals, and it's also thinking about what comes out of these processes, so the waste and hazardous waste, and the climate footprint associated with dealing with that waste. So, I'd say the chemical recycling LCAs had some problems because they often didn't include the waste and hazardous waste. But when they did, what they found was that disposal of that waste had a significant climate footprint because it's being landfilled, it's being incinerated, especially the hazardous waste. So that is associated with a large greenhouse gas footprint. And you don't see those same impacts from mechanical recycling.
Yeah, the other thing now, said I remember some of the literature compares chemical recycling to incineration, right? But we know that incineration is not a common practice, right? Like if you look at the waste and then the global practices, it's like 20 to 25% of share, right? So it's not like 100% goes to incineration. So we compare it with chemical recycling because incineration has a huge footprint. We know that. And it's whatever we're incinerated is like it's so polluted, it's so toxic, we have to capture it. So is this the right way? So to compare a process with like a 20% waste is ending up, or the right way is actually because we are not thinking chemical recycling actually gives us a new product to compare it with that. In industrial comparison in general, that's like recycle is still compared to primary still, right? Not still incineration.
Thank you so much. We are getting close to the hour mark. I think we can go a few minutes over. One question I wanted to ask you, Dr. Singla, is, well, you've both made a very convincing case that chemical recycling is not the solution to the plastic pollution problem. Would you like to just comment a little bit on what you would see as more safe and practical solutions to this problem?
Thank you so much for that question, Rachel, because it's so important, right? We know plastic production and pollution is a major problem, and we need to absolutely address it. It's harming the climate, it's harming our health. And I'd say the answer is not so simple as we just need to recycle more. Unfortunately, we're talking about a pretty complex materials system that's just integrated in our economy in so many ways. So we have to have multiple points of intervention to address this. I'm going to drop a link in the chat that was a good report, kind of looking, asking this question and looking at what's the kind of suite of interventions that we need to really try to address this problem in the next 20 years or so. And and what you'll see there is we have to look upstream to try to reduce virgin plastic production and consumption, try to ban some of the worst of the worst, like avoidable disposable single-use products, focus on safe reuse, repair, and recycling. So recycling is part of the answer, but it is one small piece of this larger puzzle, and we have to address the upstream production and the harms that come with that in order to really get at the root of this problem.
I might add, Rachel, I know we are out of time, but so here's the thing. The plastic products are never designed to be recycled. Still, right? We want the recycling work because we have waste problem, we know that. However, with the current way of their design, with all these chemicals are added, like Vina was mentioning, they are creating some toxicity problems eventually, like with the recovered product, right? So the chemical recycling processes has their issues, mechanical recycling has their issue, but we also don't have plastic products designed for recycling. That's like Vina was saying, there's so many interventions are needed. So if we look at this problem with like from the beginning, we need to have different type of plastic products that can be safely recycled if you want the recycling system.
Great. Thank you both so much. So we are a little over time now, so I'm going to hand it back to Alyssa to wrap up. Yeah, thank you all for all these questions. Sorry for not being able to get to more of them.
Thank you, Rachel. And thank you so much, Dr. Singla and Dr. Crowley, for sharing this important work. Thanks also to all our participants for your thoughtful comments and questions. We hope to see you all again on future webinars.